Bien. So we've talked about la dimension d'un espace vectoriel. We also want to talk about, now I want to talk about le rang d'une famille finie de vecteurs. Le rang. We've talked about la dimension. Now I want to talk about le rang. So let's read the definition, then I'll explain what we have here. So according to the definition, we're saying here, soit E, un espace vectoriel sur K. The last time I said what K is in this case R or C. For the purpose of this course, it is either K or C. So soit E, un espace vectoriel sur K, et F, une famille finie constituée de P vecteurs. So we have a finite family of vectors, V1, V2 jusqu'à Vp de E. On appelle rang de F et le note RG de F, or the like written all the vectors RG de V1, V2 jusqu'à Vp, la dimension du sous-espace. La dimension du sous-espace. Now let me just allow some gentlemen to join here. Like so. So, on appelle le rang de F et l'on note RG de F ou RG de V1, V2 jusqu'à Vp, la dimension du sous-espace de E engendré par F. En d'autres termes, le rang de F est égal à la dimension de vect de F. Qu'est-ce que ça veut dire? What are we saying here? So what we're saying here is, look, we've already talked about vect, le sous-espace engendré. What do we know about vect so far? We know that this vect is a sous-espace engendré. I said last time that if a vector, let's say if a vector W is in vect, if a vector W is in vect of, let's say, is in vector of a family of vectors V, this means that W is a linear combination. This means that W is a linear combination. Okay, bien. Let me just allow this gentleman to join and go back like so. If I said last time that if W is in vect of F, it means that W is a linear combination. We know what a combinaison linear is. Is a linear combination of vectors in the family F. This is what we said about le sous-espace engendré. Now, this vect is also a sous-espace vectoriel. Maybe if I didn't, tell you the other time, it is a sous-espace vectoriel of the parent space in this case, which is going to be our E. That's what I mean. That if I didn't say it last time, I'm saying it that okay, this sous-espace engendré, c'est un sous-espace vectoriel de E. C'est bon? So this is what we have. So here, what are they saying? How are they defining le rang? Le rang, they are saying, c'est la dimension. So what does dimension mean? Well, dimension means we have to count. We have to count the number of elements, the number of vectors in a certain basis, the number of vectors in a basis. That's what dimension means here. Because remember that the dimension of so far we've talked about the dimension of a basis. And then how are we calculating the dimension of a basis? Well, we are just counting the number of vectors in the base. For example, for R3, I'll look at the base of R3. Let's open the base canonic of R3. If I open inside, I'll find E1, E2, E3. There are 3 vectors. And so I'm going to conclude that the dimension of l'espace R3 is going to be 3. This is going to be true for any basis. The dimension is unique. It's going to be true for any basis of R3. So that is what I said about the dimension. So here they are saying to find the rang of the family of vectors F, I'm supposed to count the number of elements in vect of F. So this is what they are saying here. They are saying if you want to define the rang d'une famille de vecteurs V1, V2 jusqu'à Vp, I'm supposed to open l'espace, le sous-espace engendré, which is vect, and then I'm going to open, and then inside I'm going to count. I'm going to count the number of vectors for me to calculate la dimension. That's what they are saying here. Now, Let's look at how you can find the rank of a certain family of vectors. Let's look at an example. Excuse me. Let's look at an example. Let me just give you simple vectors so that we don't waste a lot of time trying to, trying to understand complicated things. C'est pas l'objectif. L'objectif, c'est de comprendre les choses. So let's look at an example here. Let's look at an example. Example like so. So let's say we have the following family of vectors. So we have the following family of vectors f, family of vectors which is u1, u2, u3 jusqu'à up like so. And then here u1 is equal to 1, 0, 2, and then u2 is equal to 2, 1, 1, like so. U3 is equal to vectors -1, -2, 4. Okay? Ça c'est -2, like so. And then U4 is, we have 2, -1, et 7. Voilà. So these are the vectors U1, U2, U3, U4. So what is the algorithm? So we're supposed to follow. Then the question is déterminer le rang. Déterminer le rang de f. Now there are two methods that you can use. The second method, we're going to understand it better when we start les matrices. When we talk about the calcul matriciel, you understand it a little bit better. The second method. But for now, we'll just focus on the first one. So for the first, we just employ the first method. Now the first method says, the first step of the first method is, you first of all pause. You're going to find some espace vectoriel. So maybe before we even do anything, in what espace are we working here? So we are working in the espace R3. So how do I know that we are working in R3? That these vectors are vectors in R3? Look at the components. U1 has 3 components. U2 has 3 components. U3 has 3 components. U4 has 3 components. So it means we're working in R3. U1 is a vector in R3. U2 is a vector in R3. U3 is a vector. U3 is a vector in R3. U4 is a vector in R3, because all the vectors have 3 components here. So I'm working in what? In R3. So that is one important thing to remember. Now the first step here, if you want to determine le rang of this family of vectors f, which is u1, u2, u3 jusqu'à up. No, here we have sorry, we have u1, u2, u3 and u4. I was writing something, a little bit more general. I thought I was writing the definition, but here it's supposed to be u4 because we only have 4 vectors. We only have 4 vectors here. C'est très important. We only have 4 vectors. So the first thing that you have to do is you have to look for some sous-espace vectoriel f of R3. Okay, you look for some sous-espace vectoriel of f of R3. So you're going to say, okay, f, which is a sous-espace vectoriel of R3. Then I'm going to say this f, I'm going to set this f, I'll let this f be equal to vect. I'll let this f be equal to vect of the vectors, which is u1, u2, and then u3, and then u4. And then the second step is going to be finding the la base de f. So the next step is, the first step is to do what? Is to find get some sous-espace vectoriel of the parent espace. Here the parent espace is R3. So I've gotten f, which is a sous-espace of R3, and then I've set it equal to le vect de U1, U2, U3, U4. Why am I setting f equal to vect? It's because here in the definition we have vect. Okay, here in the definition we have vect. So I need to introduce this vect that I have here. Then the next step is finding a base of f. Finding a base of f. But why am I finding a base of f? It is because of this, la dimension. Because la dimension is, we look at the number of vectors in the basis. We count, okay, in this basis there are how many vectors? There are 1, 2, 3, 4, 5. Now if you sum these two steps, you see that I'm writing this definition here because for step number 2, I'm finding la base. I'm finding la base, and then if I find une base, I can find the dimension. I can count the number of. I can count the number of what. I can count the number of what. I can count the number of vectors in that particular base. Okay. So let's do that. Let's try to find une base de f. Let's try to find une base de f. So we have how many vectors? We have 4 vectors: u1, u2, u3, u4. The first question that we must ask ourselves is: est-ce que c'est une famille génératrice de f? Est-ce que c'est une famille génératrice de f? Now, yes, c'est une famille génératrice. There's a theorem that we'll talk about, we'll look at a little later, but in this very session, we are going to understand. But for now, yes, c'est une famille génératrice. But for it to be a base, what other condition must I check? Hein? Est-ce que c'est libre? C'est une famille libre. Hein? That is what we're supposed to verify. So is this family of vectors U1, U2, U3, U4 libre? So that is what is U1, U2, U3 et U4 libre. So again, we'll look at another theorem that says, okay, look, here we are working in what espace here? We are working in this espace R3. And then R3, what is the dimension of R3? It is 3. So according to, so it means la base of R3 has how many vectors? Has 3 vectors. There's a theorem that we're going to talk about a little later that says if I have a family of n vectors, here, if I have a family of n vectors, I have a base B, okay, the base of here, the base B is the base of R3, which has 3 vectors. Since here I have 4 vectors, automatically this family of vectors cannot be what? Cannot be libre in R3. This family of vectors cannot be libre in R3 because I've sort of like I've exceeded the number of vectors in this given base, which is B, la base de R3, which is generated by 3 vectors. So this family of vectors cannot be libre in R3 because there are 4 vectors here. So the algorithm says that, okay, if this family of vectors is not libre, so here the first answer here is no. No, it's not libre. No, it's not libre. Why? There are 4 vectors here, but if you look at R3, it is engendré par 3 vecteurs. If you look at the base of R3, it is engendré par 3 vecteurs. So this family of vectors cannot be libre. We'll talk about this theorem a little later. Okay? So if it is not libre, then you are free, then you take out one of these vectors. So I'm going to take out the 4th one. I'm going to take out the 4th vector. So if I take out the 4th vector, then I'm going to have this family of vectors. If I take this out, I'm going to have this family of vectors, U1, U2, U3. Now there are 3 vectors here. So here I won't conclude directly that, okay, this is, if I ask the same question, is this libre? So to be able to prove that this is libre, I have to find, yes, Natasha?
So you just take out the vector, the 4th vector.
By chance.
Why have you taken it?
So it is because I want to come up with a family of vectors that is libre. So the algorithm says you can take out any vector. If you find that it is not libre, you can take out any vector. So here it is not libre. Here the answer is direct because the base of R3 has R3 is generated by 3 vectors. Okay, R3 is generated by 3 vectors, and so any family of vectors U1, U2, U3, U4, any family of vectors that has more than 3 vectors, in the case of R3, any family of vectors that has more than 3 vectors cannot be a base of R3 because it cannot be libre. You understand? So you take out any vector you want. Yeah, here I've just taken out U4. You can take out U1 if you want. You can take out U2 if you want. You can take out U3 if you want. So I've just taken out U4 such that I remain with U1, U2, and U3. So how do you show that this family of vectors is libre? You use the same definition we used the other time. You find scalars alpha beta, gamma, like so. You find scalars alpha, beta, and gamma, and then you take a linear combination of these vectors. So you say alpha u1 plus beta u2 plus gamma u3. You take a linear combination of these vectors. You suppose that it is equal to 0, and then try to find what is alpha, then what is beta, and then what is gamma. If you find that any of these quantities is not equal to 0, then it is not libre. So I've already solved this problem, but I'm going to give you a chance to solve this. At your own time, you can rewatch the video, or you can, at your own time, try to solve. But then the answer here is no, it's not libre. Again, it's not libre. So again, here the answer is no. I've already solved this particular problem, so you can solve, you can verify, because you already know the method to employ here. You already know the method. Take a linear combination, suppose it's equal to 0, find alpha, find beta, find gamma. One of these will not be equal to 0, so it cannot be libre. So again, you do what? You take out any vector. You take out any vector. So here, I'll take out this one. If I take out this vector, I'm going to have u1 and what? And u2. Yes, this is going to be libre. Yes, this is going to be libre. So yes, it's going to be, this is going to be equal to libre. This is going to be libre. This is going to be libre. If you check, if you perform this calculation, alpha 1 u1 plus alpha 2 u2, like so, is equal to 0. You find that alpha 1 is equal to alpha 2 is equal to 0. So this means that it is libre. So we found a family of vectors that is libre. We found a family of vectors that is libre. So finally, the rank of the family of vectors f is equal to the number of vectors in this family of vectors that is libre. So here it's going to be equal to 2, like so. So let me just repeat the method. Of course, we'll look at more examples. We'll look at more examples. We'll look at more examples here. So le rang est égal à 2 in this particular case. So the first thing that you want to do is you look at all the vectors you have. Then I also identify that we are working in yes, Violet.
How does that agree when our R has 3?
How does it agree when our R has 3?
Yes, since our base is down to 2 vectors, but R is 3.
So yeah, I understand the confusion, but we'll look at the theorem a little later that is going to help us understand the aspect of génératrice and libre. So the idea here is, the idea is if you have a family of vectors, if you have a family that has n vectors, if you have a family that has n vectors, okay? Maybe let me just go to the theorem quickly before we even look at it. So up. Yeah, let's look at this theorem that is here. Let's look at this lemma that is here. Soit E un espace vectoriel non réduit à 0 et M un entier un entier naturel différent de 0 si E admet une famille génératrice G de cardinal M, alors toute famille de M plus 1 vecteur ou plus est liée. Maybe this one it's not very clear, but I have this remark and this theorem that I have here. So let's read this proposition. Soit E, en cas espace vectoriel, admettons une base ayant n éléments. So we have an espace vectoriel E that has how many elements? N elements. So in other words, here we have this. We have une base that has n elements. Une base that has n elements. So this is B. It has n elements. So let's say B1, B2, B3 up to Bn, like so. So the first property is saying toute famille libre L de E a au plus n éléments. So any family that is libre, any family that is libre in this espace which is E, any family of vectors that is libre in this espace E is going to have at most n elements. So if L is libre, if L is a family of vectors that is libre, then it has at most at most is supposed to have how many elements? N elements. If it has more than n elements, then it cannot be a family of vectors that is what? That is libre. So if you go back to our problem, the problem that we have at the moment, this family of vectors that is libre, yes, it's accepted, because if you look at R3 has how many vectors in its base? If you just maybe look at la base canonique, you see that R3 has 3 vectors, E1, E2, E3. So meaning any family of vectors that is libre in the espace R3 has to have any family of vectors that is going to be libre in this espace that we are seeing here, R3, has to have at most how many elements? 3. I mean at most 3 elements. So if I have 2 elements, yes, that family can be libre. That is why we even disqualified the first part here, because in the beginning in the Genesis we had how many vectors? We had 4 vectors. So this family of vectors where we have 4 vectors, this family of vectors cannot be libre because we have 4 elements. Okay, 4 elements. I mean we have 4 vectors. So we kept on reducing. Here we have 3 vectors. We know that we can have at most 3 vectors, yes. But then the conclusion for the second one is not immediate. We have to verify through this linear combination. For this one, you find that, okay, these are liés. So you take out 1 vector. So this one is accepted. Look, here we're not talking about the dimension. We're talking about the rang. The rang is la dimension du vecteur. C'est la dimension du vecteur. Okay, c'est la dimension du vecteur. So this has nothing to do with the dimension of R3. I mean, this value 2 here is not indicating the dimension of R3. No, it is indicating the dimension of le sous-espace engendré par this family of vectors, which is F, that we have here. And it's not the dimension of this vector that we have here, F. So we can accept that this is this is acceptable because we know that for any family that has to be libre in R3 has to have at most 3 elements. This family has 2 elements, so yes, it can be libre. It is possible that it is libre. We will verify through the linear combination. So we verify through the linear combination. We find that everything is working. Yes. So this is what we have here. So that is the theorem that we're going to, discuss a little later. Is it clear? Bien. So where was I? I was here. So this is how we can calculate le rang. Yes, Natasha.
Sorry. I want to ask again. So the fourth, for 4 vectors, it has refused, but for 2 it's okay.
Mm-hmm. Because if you look, R3 has a base, right? R3, the basis of R3 has how many vectors? The basis of R3 has 3 vectors. E1, that is, if R3 has many basis vectors. But let's consider la base canonique. How many vectors are in la base canonique? There are 3 vectors in la base canonique. Now apply this theorem. Apply this theorem that we have here. Soit E, en cas espace vectoriel, admettons une base ayant n éléments. Alors, toute famille libre, L de E, a au plus n éléments. So, where n is the number of elements in the base, let's look at R3. R3 has how many basis vectors? It has 3 basis vectors. If you take la base canonique as an example, we have 3 vectors, E1, E2, E3. So meaning, any family of vectors that is going to be libre in R3 is supposed to have at most how many elements? It's supposed to have at most 3 elements. So if I have a family of vectors that has 4, if I have a family of vectors that has 4 vectors, then it cannot be libre in R3. You understand now? It cannot be libre in R3 according to this theorem, or according to this proposition. That family, that's why we rejected the one with 4 vectors, because it cannot be libre in R4. In R3, because we have 4 vectors. Any family of vectors that is going to be libre in R3 is supposed to have at most 3 elements. So for the first set U1, U2, U3, U4, You don't even have to check through the linear combination. You can straight away reject it using this theorem that we have here. You can reject it using this theorem that we have here. So this is what we have for le rond. This is what we have for le rond. So we'll look at more examples of how to find le rond. In other words, it is in the vect, in the espace vect. If you have vect of the families, you can keep on taking out the vectors until you land on a family of vectors that is libre. You can keep on taking out the vectors from vect such that you have a family of vectors that is libre, and then that is going to be the number of those vectors is going to be le rond. So the takeaway here is this: if you want to find le rond of a certain family of vectors f, so you have to look at vect of those, vect of that family of vectors, and then the goal is to find une famille libre. So you can basically be taking out vectors such that you remain with a family of vectors that is going to be libre. That's the idea here. We'll look at more examples and then you're going to understand these things better. Again, this is about le rond, but then we'll talk about this later, a little later, because there are some things that you're supposed to understand before we even understand what is presented here. So there are some things you are supposed to first of all understand. There are things that you're supposed to understand. Now here you have to listen attentively. You have to pay attention to what I'm going to say. So this is a very, very important theorem. Now we're not going to prove this theorem, like we're not going to write the formal proof, but I'll explain this theorem in form of an algorithm. I'm going to explain this theorem in form of an algorithm because you're going to understand it better that way. You're going to understand it better that way. So I'll explain it in terms of an algorithm. So it is known as le théorème de la base incomplète. Le théorème de la base incomplète. Alors, so what is the theorem saying? Donc, soit E, en cas espace vectoriel, admettons une famille génératrice G, which has vectors G1, G2, and Gm. Alors, so we have a family, we have en cas espace vectoriel, which is E in this particular case. And then we have this family, this espace E has une famille génératrice. It has a famille génératrice, which means this family, it has a famille génératrice G that has vectors G1, G2 up to Gm. So meaning this family of vectors can generate the space E. That's what they are saying, in other words, that this family of vectors G is going to generate E. That's what they are saying here. Then the first remark or the first point here is that la famille génératrice G contient une base de E. Contient une base de E. So if E, we have an espace vectoriel which is E, and then we have a famille génératrice which is G. Okay, this famille génératrice is going to is generating the espace E. And then they are saying the first point is that la famille génératrice contient une base de E. It means, okay, this same famille génératrice that can generate this E, this same famille génératrice G that can generate this E that we have here contains a basis vector of this parent space which is E. That's what they are saying here. So how can we think about this one? How can we think about how do we go about thinking about this one? So from the previous, you can connect it with what we're from doing here. So yes, this famille génératrice G is going to contain une base de E because if you look at what we are doing with vect, we said if this family génératrice of families G1, G2, Gm is not libre, because a base, it's already G is already a famille génératrice, right? For it to be a base, let's say if G is supposed to be a base, what condition must I check? So who can tell me the condition I must check for me to conclude that G is a base? So what am I supposed to do for me to conclude? Here they are saying soit E en cas espace vectoriel, admettons une famille génératrice G. So G is already a family génératrice of E. What is missing for G to be a base? So who can tell me what is missing for G to be une base de E? Yes, Natasha.
I'm sorry, is it if it's libre?
Yes. So we're supposed to verify that this family of vectors is libre. So if the family of vectors G1, G2 up to Gm is libre, what am I going to do? Then straight away, G is going to be une base de E. So we see that in that case, what they are saying here for point 1 is actually going to be true. But what happens if the family of vectors G1, G2 up to Gm is not libre? So it means just like what I was doing for vector, I can take out one vector at a time. If it is not libre, it means it is lié. It means that there's one vector inside that can be written as a linear combination of the other vectors. Okay? So if this family of vectors G1, G2 and Gm is not libre, if it is not libre, then I can take out as many vectors as possible, so such that I have a family of vectors that is going to be libre. So in other words, if I keep on taking out if I keep on taking out the vectors, I'm going to have a family that is B, okay, because I've removed some elements. It's no longer G. I'm going to find some new B that is going to be contained in G, such that this B is going to be a base, is going to be soit une famille libre et génératrice de E, such that it is going to be a base. Is the first point clear? G is already une famille génératrice. So for it to be a base, we have to talk about the idea of libre. Okay? So if G is not libre, it means it is lié. Meaning inside there's a vector, let's say maybe G2. For example, G2. That can be written as a linear combination of the other vectors in G1. In G. But so it means we can take that vector out, or we can take a vector out such that the vectors that I have inside are going to be libre. So you can see that the size has changed. It's no longer G. If we take out a vector, it's no longer G. It is going to take a new name. Here we'll be calling it B. Okay. Then B is going to be contained in G, because G has all the elements of B, and then G has all the elements of or G will have all the elements of B, but then B will be missing a few elements of G. So they are correct here by saying B is going to be a subset of G. So that's how you think about this first point here. That's how we can go about this first point that I have here. Is it clear? Is the first point clear? The first is one clear? Do you understand one? Right. So let's look at the second point. So for the second point, they are saying toute famille libre, elle, peut être complétée en une base de E. C'est-à-dire toute famille libre, elle peut être complétée en une base de E. C'est-à-dire qu'il existe une famille F in G telle que E union F soit une famille libre et génératrice de E. Now, still, if you think about a base, a base satisfies two conditions, right? A base satisfies two conditions. The first condition is it is a family of vectors that is going to be libre, and then secondly, it's going to be a family of vectors that is going to be génératrice. Okay, here they are saying if I get any family of vectors that is libre in E, but then that does not satisfy the second condition of génératrice, I can now add vectors. I can add vectors to that family of vectors that is libre, such that I'll keep on adding vectors to this. I'll keep on adding vectors to this new family of vectors, which is L. I'll keep on adding vectors such that I get a famille that is à la fois génératrice et libre. That's what they are saying here. For the first point, they are saying we can keep on removing from G. But then I can also keep on adding vectors in this family generatrice for E, G is a family generatrice for E. It has vectors G1, G2, Gm. So I can keep on adding the vectors G1, G2, Gm in any family of vectors that is libre in E, such that it becomes generatrice. So that also so that the family L also verifies the two conditions of libre and generatrice. Because at the moment L only verifies one condition, which is libre, but it also has to verify generatrice for it to be a base. So I can keep on adding vectors to L, the vectors from G, I can keep on adding them in L, such that I arrive at, so it's an algorithm. You keep on adding, and then you verify that, okay, the vectors remain, the family of vectors remains, stays libre, and then you keep on adding until it becomes generatrice. Keep on adding until it becomes generatrice. So for the second point, you keep on adding vectors to a family of vectors. You keep on adding vectors in G to any family that is libre, such that it becomes generatrice and libre à la fois, for it to be considered a base. For the first point, we are saying you can remove vectors from G such that it becomes libre. You understand? Is the theorem clear? Is what the theorem is it clear? So remember this idea. Just remember this theorem the way I've explained it to you. Now, due to time, I won't write everything I was saying, but maybe later on you can rewatch, you can rewind the video, you can repeat this part, as long as you sort of do not get the concept and all that. Okay, so that's what the 2 points are saying here. So that this is what we have. So c'est le théorème de la base incomplète. So I've explained it in terms of an algorithm. C'est clair? Je passe? Is it clear? Can we make progress? Is it clear? Natasha, is it clear? Okay. Violet, is it clear?
Yes, it is.
Yeah. So remember that I said this. I want us to solve the last exercises that we have. The exercises that we have here, maybe 2 of them and all that. But then we have to discuss a few things here. So I won't write theorem de la base incomplète, the algorithm I was talking about. This theorem, I've already talked about it. I said, we'll look at this part here, that all you have to do is remember this proposition. Always remember this proposition. Always remember this proposition. Always remember this proposition. That soit E en cas espace vectoriel, admettons une base ayant n éléments. So if I have an espace vectoriel that has a basis that has n vectors or n elements, then toute famille libre L de E a au plus n éléments. So any family of vectors that is going to be libre is going to have at most n elements. Okay? It's going to have at most n elements. If I have n plus 1 elements, then that family of vectors cannot be libre, because the base has n vectors, and if this family of vectors that is libre, and if this family of vectors L has to be libre, then the maximum number of elements it can have is n, which is equal to the number of elements in the base. We used it when solving the problem on le rond. Okay, we used it there. So if I have m plus 1 elements, yes, it can be generatrice. Generatrice, yes, it can be. Because generatrice, the condition for generatrice, yes, is going to be satisfied. However, libre, it is not going to be libre, because for a family of vectors to be libre, if we have a base that has n elements, then the maximum number of elements in that family of vectors has to be n, the maximum. So it can have n minus 1 elements, n minus 2 elements, n minus 3 elements. Yeah, it cannot be more than n. The number of elements cannot be more than n. It cannot be more than n. This is what this theorem is saying. Now again, we won't say anything. We won't prove this theorem due to time, because I want us to, due to time, I won't be able to go through the proof. But the proof is simple, because we now let's look at this part here. Now let's look at this part here. Well, we're talking about le rond. Let's understand what is presented here. Let's understand what is presented here. Now I can see that Violet has left the meeting. Are you able to get what I'm saying, or am I skipping? Or maybe it's a network problem on our end?
No, I think yes.
Yeah. So I think it's just a connection problem, or I mean, yeah, on her side. So let's understand now that we know what is happening here. Let's understand what we have here. Donc let's understand what is written here. Now let me just check. Just give me a moment. Okay. So, soit E en cas espace vectoriel, si V1, V2 jusqu'à Vp désigne des vecteurs de E, alors le rang, we have this family of vectors. And then here they are saying le rang de cette famille, the rang of this family of vectors, V1, V2 jusqu'à Vp is less than or equal to P. Now, what is P in this case? You can see that P is the number of elements in this family. So we have a family of vectors V1, V2, V3, and then V4, and then V5 up to Vp. So P is the number of elements. So here they are saying that the rang of this family of vectors is less than or equal to P. Is less than or equal to P. Now, how do we process this? Remember that le rang is going to be equal to the dimension, is equal to the dimension of vect, is the dimension of vect of this family of vectors V1, V2, V3, and then Vp, like so. Remember what we are doing here. We will keep on the goal is to look for a family of vectors that is what? That is libre. So we check, is this family of vectors libre? If it is not, we'll keep on removing the vectors. We'll keep on removing the vectors. We'll keep on removing. So if this family of vectors is not libre, we'll remove Vp, for example. So we'll have Vp, we'll have vectors from V1 up to Vp minus 1. So again, we'll keep on removing until we find the family of vectors that is going to be libre. So we can understand why here they are saying that le rang is going to be less than or equal to P. Because it is from this family of vectors that we start. We look for a family of vectors that is libre. So if it is not libre, we'll reduce the number. So we'll have a number that is less than P. So at most, the rang is going to be equal to P. That is, the family of vectors, this entire family of vectors is going to be what? Libre. So we can understand this first point. I mean, this first idea that we have here. Okay? Now let's understand the second one. De plus, si E est de dimension finie, avec la dimension de E est égale à n, alors le rang de V1, V2, Vp is going to be less than or equal to the minimum of n and p. So what is n? N is the dimension of E. Now we know that the dimension of E is equal to the cardinality of B, which is going to be une base. Okay? We know that the dimension of E is going to be equal to what? Is going to be equal to the cardinality or the number of elements in B. Now remember that le rang de V1, V2, V3 jusqu'à Vp is going to be equal to, c'est la dimension du sous-espace, engendré par the same family of vectors. So by vect of V1, V2, V3, V4 jusqu'à Vp. That's that's the definition of Laurent. What do we know about this vect? Oh, this vect that is here. This vect that we've seen here. This vect that we've seen here is un sous-espace de E. It's a sous-espace vectoriel. Et c'est un sous-espace. So c'est un sous-espace vectoriel. C'est un sous-espace vectoriel de E. And then we know that if we have some vector f that is included in E, if we have some vector f that is included in E, such that f is un sous-espace, c'est un SEV de E, then the dimension of f is less than or equal to the dimension of E. And then if f is equal to E, this is going to be equivalent to saying that the dimension of E is equal to the dimension of f. So if you look at this first situation that we have here, we see that if f is a sous-espace vectoriel of E, then the dimension of f is always going to be, the dimension of f is less than or equal to the dimension of E. If the dimension of E is equal to if the dimension of f is equal to the dimension of E, then it simply means that f and E are the same espace. Okay, f and E are the same espace. So you can see that that in any case, the dimension of this sous-espace, vectoriel is going to be less than or equal to the dimension of E. So here, if you look at what we have here, the dimension of E is n. The dimension of E is n. And then here we are saying that this vect that we are seeing here is a sous-espace vectoriel of E. So this is our f in this case. So this vect is a sous-espace vectoriel of E. So it must be that the dimension of this espace, which is vect, the dimension of this espace vect that I'm seeing here, is supposed to be less than or equal to the dimension of E. So what is the dimension of E? The dimension of E is n. So it means that the dimension of this f that I'm seeing here is supposed to be less than or equal to n. Okay? So in a nutshell, we see that we have n and p, meaning this rho has to satisfy the two conditions. It has to be less than or equal to p. It also has to be less than or equal to what? To n. Okay, it has to be less than or equal to both of these. So if I take the minimum, the smallest of n and p, and if Laurent is less than the smallest of the two, then that is going to make sense. Because there's this condition that we are supposed to check, and then there's the condition for n. So if I take the smallest of the two, then the two conditions will be, everything is going to be okay. You understand? At least what is presented here. The first one here, we are saying Laurent de V1, V2 jusqu'à Vp is going to be less than or equal to p, where p is the number of elements in the family of vectors. Now, if you remember what we were doing in the algorithm, we started with the given family of vectors. Is it libre? If it is, yes, then the rho is going to be equal to the number of elements, which is p. Now, we'll keep on removing vectors from this family of vectors until we find the family of vectors that is libre. So the number is reducing. So at most, this rho can be equal to p. And then here, for the second one here is, for n, we know that vect is un sous-espace vectoriel de E. If you apply what I've written at the bottom here, you see that the dimension of this vect here is less than or equal to the dimension of E. So meaning the dimension is less than what? Is less than or equal to n. Now, the dimension also has to, the dimension is less than or equal to n because vect est un sous-espace vectoriel de E. Now, we're supposed to satisfy, the rho has to satisfy the first condition and the second condition. So if I want to satisfy both these conditions, I'll take the smallest number. I'll take the smallest of n and p. Then the two conditions will be checked. Is it clear? Is it clear?
Wait, what is n? VP.
What
N
is
what?
I didn't get your question.
Number. It's a number of vectors.
P
N.
n
Yes.
n is the dimension of E. According to what they are saying here, n is the dimension of E. So meaning it's a number of vectors in the bars of E. Here I've got the bars, which is B here. So dimension of E is equal to the cardinality, or the number of elements in a bars of E. So due to time we won't try, but you can understand what they've presented here. I mean, I've explained what they've presented here, sort of like trying to think about what we've already covered, and we apply it here. We can understand these expressions, why the expressions are like this. C'est clair?
Well,
Okay. Théorème de la base incomplète, we've already talked about this. This one we already talked about that. This one, yes. This one we've already talked about this. When you have n vectors, you just have to show libre and all that. So, bien. So now we'll talk about somme de deux sous-espaces vectoriels. Somme de deux sous-espaces vectoriels. And then finally, we'll finish up, what we've discussed. And then there are exercises at the end that we'll have to solve. So I can see that we have under 9 minutes. So what we're going to do is that we're going to exit this one. And then I'll send you a new link. Then you'll be able to join from that new link. So you can exit this one and wait for the new link.